This work for everyone? Sounds good? All right, hi, I'm Joe Doliner. I am CEO and founder of Pachyderm. My co-founder, Joey, is also here today, and it's his birthday, so you should all make a birthday. I did actually have to do that. It's in the contract we signed. So I'm here today to talk to you about big data applications with containers, which are a hot new technology that I'm assuming you guys have all heard about at least a little bit. But so who's heard of a container? Just so I can take. Okay, I wasn't wrong. People have heard about containers. Would anybody like to just throw out a quick description of what a container is?
It's a pristine environment.
It's a pristine environment. Oh, that's a very poetic description of what a container is. Yes, that's also a great description. A container is like a pristine environment. Particularly, it's a pristine environment for your program to go in. And the reason that putting your program in a pristine environment is a good thing is, well, I mean, one, it's your program, so you kind of like a pristine environment for it. But two, this means that your program isn't going to have any other weird state messing with it. It's going to run the same way every single time. And that's very handy in a number of cases. So first, just a little bit about myself. I worked for 4 years at Rethink DB, along with Joey. And then I did my time running the Hadoop infrastructure at Airbnb and learning about a bunch of big data applications there. And now I'm on Pachyderm, where I'm building more big data applications. So what is Pachyderm? Pachyderm is a way to do big data with containers, first and foremost. And the idea here is that, containers are this great way to write applications, but you need a little bit more than just a container framework to do big data applications, because you need to figure out how to marshal around all this data. Pachyderm does that for you. And it does it in this very particular way, which stems from the fact that Pachyderm implements version control for data. So who here is familiar with Git, the version control tool? I expect many of you. Okay, so Git, as we know, is this really nifty tool where you can basically take these snapshots of your code, right? And this is super handy because this lets you see what the state of your code looked like yesterday. It lets you roll back to known good versions if something goes wrong. Well, Pachyderm lets you do that same thing with huge data sets. So you can have a petabyte data set in there that's snapshotted granularly every single day, every single hour, and we give you those same types of semantics. Second, as we've mentioned many times, Pachyderm uses containers for data processing. That's the core unit that we give you to implement your programs. And we do that because it's this incredibly flexible unit. You can put whatever you want in your container. And so Pachyderm is out of the box compatible with all of the libraries that you can find on Linux, all of the utilities, all of it just works. Another thing that Pachyderm does is that it very effectively blurs the line between batched and stream processing. Now, as we know, sort of batched processing is when you've got like a big pile of data somewhere and you just tell something to churn through it and come back to you with the results. Stream processing is when you've got this data set that's changing over time and you want to sort of keep your results up to date as new data comes in. Because of the way we think of data, because it's version control, we always understand how the data is changing, and so we can unify the approaches to batched and streaming computation inside of Pachyderm. And the demo that we're going to do is going to show you that. Lastly, Pachyderm is built on top of object storage. And so what that means is that sort of all of the notions of like allocating disk drives that you have to do and stuff in cloud providers, you don't have to deal with any of that because it's built directly on top of S3. And so you can have Amazon administer that infrastructure for you, and the storage layer is just taken care of by them. And lastly, I just want to say that Pachyderm actually shares no code with Hadoop. That's something that people get confused on from time to time, so we say it explicitly now. This is a completely new project. It just is seeking to sort of fill the same need as Hadoop. Okay, so we've already talked about containers as this pristine environment, but first off, we should say here, we've already talked about why they're used for big data applications, but there's a new word on here, which is Kubernetes, that I haven't mentioned at all. So has anybody heard of Kubernetes? Let's let someone else answer, right there.
So, what do you expect? Yeah, it's a project led by Google. I mean, that's almost their third generation orchestration framework for their data centers, and they have open sourced it and trying to drive that a much broader community.
Absolutely.
It's fairly cloud neutral. can deploy on AWS, Azure, and obviously GCP.
Yep. So that was a great explanation of it. Kubernetes, it's this third generation orchestration tool from Google. It's completely open source. It's based off of Borg, was the name of the internal tool. And it basically is this framework for managing containers, right? And it lets you orchestrate your containers in all these very high-level ways. It lets you say that, I want this service to just run somewhere in the cloud, and Kubernetes figures it out. It lets you say, run this job here and tell me when it's done, and Kubernetes figures out all the details. It's this incredibly powerful orchestration piece that Pachyderm actually builds on top of to accomplish what we do. So, first off, version control for data is sort of an interesting concept all by itself, right? There's several things that you can do that you can learn about your data if you don't, if you have version control that you can't get in a system that is just, gives you like your data as a single state. First off, you can view the diffs for this data. And that's a very, very important thing in data science, because being able to view the diffs tells you how things changed and lets you answer the questions like what happened last night that caused this number to spike up a huge amount. These are the questions that we ran into all the time at Airbnb. Second thing that it lets you do is it lets you collaborate effectively. Now, this was a problem with data science that wasn't immediately obvious to me until I started actually working in the industry. That we have these huge problems where two data scientists would sort of start stepping on each other's toes because they were each using the same data sets. And so what started happening was every single time a data scientist started doing a project, he or she would just fork the data and make their own copy of it in HDFS. And what this led to was a huge disagreement between all our data scientists about like very simple things in our company, like how many users we had, how many listings we had, because everybody was working off of this different forked data set. And so that was the problem that initially provided sort of the impetus for building this collaboration right into the data layer. Because when you have Git-like semantics in your data layer, you can actually fork. You can have all the users say, okay, we're pointing at this, but this is my forked copy of it. Nobody's going to mess with it. And then you can later pull in new data just like you do with Git to catch your analysis up to the new stuff that's happened. And that brings me to sort of the last thing that we really get from version control, which is data provenance. Everybody's familiar with the word provenance, right? It means sort of tracking the origins of. We would have a huge problem with this at Airbnb. We'd have no way to see exactly which data set our results had come from. And so we'd oftentimes have to rerun analysis just to see what things look like on a specific day. Okay, so now changing gears a little bit, let's talk about some of the things that you can do with a containerized data pipeline. So first off, the cool thing here is we've got this code in a container, and we can just run it on some data, output it somewhere, but we can actually do so much more than that with our system. First off is you can build dependencies between jobs. A job can process something, output results, and then other jobs can get kicked off on the output from that first job and process that again. And with this, it grows into, at any company, this massive network of thousands of jobs that all sort of feed data through and compute all the things that are important to your company. And Pachyderm orchestrates that whole system for you. The pipelines that we run in Pachyderm, they're actually triggered by the changes in the data, right? So as new data comes in, we can find those diffs because of our version-controlled system, and we can make these, and we can kick off the pipeline such that the data is just constantly piping through them. So we actually have come to think of this more of as a DAG of data that needs to be produced in certain places. And this leads to a number of benefits. One is that you get a huge amount of processing efficiency. And the reason for that is actually this other concept which is called incrementality, where because of your diffs, you can see that I'm trying to compute this new data set, but I already computed 99% of this yesterday, and there's only this small 1% diff that needs to be computed again. And Pachyderm can just take out that 1% diff and compute on that instead, and give you the results much faster. So tying it all together, this is sort of the picture that we want you to have for Pachyderm. And this is basically what we call the data lake use case for Pachyderm. Right? Data lake is a word that's thrown around a lot in the Hadoop ecosystem. We use it in Pachyderm as well. It basically means this system that you can dump data into and process it and then get data out of it. And so you can see you have sort of these dumps of outside data from production databases, they come into our file system. Pipelines can run over that and become new applications, and then they can also kick them out into warehouses, data warehouses to be processed in different ways.
Can you give some examples?
Some examples? Yeah, so examples of this that we would use a lot at Airbnb is, for example, we dump our production database every night, and then that would become this big machine learning pipeline that we use to compute fraud, right? And every single night, the pipeline would churn away, and out of it would come this gigantic machine learning model that would detect fraudulent transactions during the day. And actually, this was an example of one of the problems we would have where occasionally something upstream of this job would break, and this would lead to a cascading failure where the model would actually come out empty because sort of jobs didn't notice that the previous ones had failed. And so we'd wind up with a machine learning model that wasn't detecting anything, and we'd just be bleeding cache that day. And so this is one of the really advantageous things about version control is, again, you can roll back things immediately, and you can see when something has failed and not commit it because everything's transactional. Okay, so that's the concept, and now we're going to demo it to you live with Pachyderm. So basically what we're going to do here, do a quick walkthrough, is we're going to do, and there should be an R there for streaming data pipelines, not steaming data pipelines. So basically what we're going to do here is we're going to run like a little faux big data business for a fruit stand, and big data in quotes here. This is a fruit stand where we have sort of transactions coming in, and we're going to create a processing pipeline to sort these transactions and then sum up to see how much of the various pieces of fruit we're selling. And it should be fun. So I'm going to take us over to the terminal where I have things set up. So, all right, let's figure out how to make this work. It seems to be cut off. Well, we'll just solve that way. So, first off, I'm going to show you a view of Kubernetes here, just to show you what I have running. Kubernetes, as I mentioned, is the scheduler. On it, we already have. Oh, it's cut off in the other direction, too. Is there anything we can do about that?
I haven't seen that issue before.
Well, we can maybe...
Yeah, make the window smaller. Maybe. Does that work?
That'll work.
Okay.
So what Kubernetes is showing me here is that I have a couple of services scheduled. I've got these two Pachyderm pods that are running. And a pod is a Kubernetes term basically for a container that has been scheduled. So I've got two instances of Pachyderm running. I'm running in a sharded setup. I've got a database right here in DB, and I've got etcd, and then this is stuff that Kubernetes did. And we're going to come back to these views later as Kubernetes adds more and more stuff there. And then I've also got a way to interface with Pachyderm that is called pack control. And so I'm going to show you here a view of repos, and you can see I don't have any repos in Pachyderm. So first, what is a repo? Well, we've made all of the semantics in Pachyderm borrow the naming from Git. So repos mean the same thing, commits mean the same thing, files, of course, mean the same thing. And so if we're starting out in Pachyderm, like in Git, the first thing that we need to do is we need to make a repo so that we can put something in it. Okay, so I'm going to create a repo for us here. And I'm just going to call it data. And we're going to put, as you might guess, in it, data in it. So now I have my repo for data, and if I want to write anything to it, then I'm going to need to also start a commit to put stuff into it. So, and I'm going to type master here because I want this commit to be on a master branch. And so now Pachyderm has created a commit, and I can show you that commit. And that's getting wrapped a little bit weirdly, but you see I have a commit, it's on master, and its size is 0 bytes, because I haven't put anything into it yet. So why don't I put a little bit of data into there? So first off, let me show you the file. This is an example file of the sales data I get out of my fruit stand. As you can see, it's very, very simple. Each line is just the name of a fruit, either orange, banana, or apple. And then there's a few spaces, and then there's the number of that fruit that I sold in the transaction. And I'm going to take this file, and I'm going to put it inside of my commit, inside of my repo. And I'm going to put it in a file called sales. And now the last thing that I need to do is I need to tell Pachyderm that this commit is finished, and it should make it immutable and make it part of the history. And now when I do this command, move up, I can do this. I can see that there's actually some data inside of the repo. Okay, so all I did was I got some data into Pachyderm. Easy. Now for the fun part. Now I'm going to actually run something on this data, and I'm going to see the results come out. So I'm going to open up a pipeline file for you here. And a pipeline file, as we were talking about pipelines, is this series of transformations over your data. The pipeline file is the thing that defines one of those. This is a pipeline. Is this a good size, or should I make this a little bigger? Good size? Okay. So, you can see here first I've got a name for this pipeline, and this is the filter, or a name for this step in the pipeline, and this is the filter step. And what the filter step is supposed to do is it's going to take this data that it finds in sales, and is going to split it up into a file for apples, a file for bananas, and a file for oranges. And so the thing that defines, that actually describes what it does, that implements this, is this transform field right here. I mean, you can see first, I've got the image, right? And as we mentioned, everything is going to run in a container. So the fruit stand image is the container that I made for this demo. It's actually basically just a stock Ubuntu image, because all I'm using is like shell and grep, but that's where I put my application. The command I'm running is just shell, and what I'm passing it is these three lines that are calls to grep. Now, you'll notice that I'm accessing the data here in a very interesting way. I'm actually reading from the local file system in the path/pfs/data. And this is sort of the secret sauce to how the whole system works, is that when Kubernetes creates these jobs for us, we put the data for the various pieces of the file system into your local file system by way of a fuse layer. And so with this method, what we can do is we can spin up one container that will just see the full sales document in one spot, or we can spin up 1,000 containers, each of them seeing only a subset of the sales in that spot. And so we can automatically parallelize these operations, even though they're just accessing what looks to be like the local file system. And then, of course, when I read the data out, that's also into the local file system. That's in a place called pfs/out. And then I've got, moving on, I've got parallelism here, which is how I would actually scale up the parallelism of this job. So if I put 10 in there, Kubernetes would actually run 10 copies of this job in parallel. And lastly, I'm declaring the inputs into this job, which is just my data repo. Does that make sense to everyone? All right. So now I've got a second stage in this pipeline, I'll scroll to, which is the sum stage. And you can see it's mostly similar. It's inside of the same image. I'm using shell again. But here my command is doing something a little bit different. And does anybody happen to know their awk well enough to know what that is doing? This gives you a big hint. The name gives you a big hint. This is basically saying, take what you find, sum it up into the register S, and then at the end, print out S. So it's just summing up a bunch of numbers, which is what we want, because we want to sum up this count of things. And this again has got a parallelism of 1, and then finally, you'll notice that the repo that we're taking as input is filter, which was actually the name of a pipeline above. You can just reference pipelines by their name in here too, to sort of chain operations together. So this is actually a chain pipeline. Any questions on that? All right, let's stop talking about it and actually run it. All right, so I created the pipeline, and then I did pack control this job immediately afterward. I did it immediately afterward because I was hoping to get in there before those before it turned to success while the jobs were actually running, but I didn't do it fast enough. So what happened here? Well, it fired off these two jobs, and as we can see, these two jobs were outputting. One was doing filtering, one was doing sum. And they were outputting to repos that they actually created to service the pipeline. So as we can see, we now have 3 repos. And the filter repo is about the same size because it wasn't filtering anything down. The sum repo is much, much smaller because if you remember, the files in there actually, it was just writing a single number in there. So I'm actually going to give you a look at what it actually wrote using the mount command. So, one second to set this up. What mount does is it actually mounts that fuse volume that we were talking on your local host. So by doing that, I now have this directory /pfs. And in this, I've got a folder for each of the repos that I had in PFS. And then within each of those, I've got a folder for each of the commits that were available. And so if I look inside of my sum repo, in this commit, I can see that I've got apple, banana, and orange, which were the files that I was expecting. These are my sums. And so I can just cat these. And I can see how many of each fruit I sold. So I can see I sold 133 apples, I sold 165 bananas, and, well, I won't do orange, but we sold some number of those too. And so the results have been materialized for me in this sum repo. Does everybody understand what's going on here? Good? Okay. So now for the last step. We've got this pipeline installed on a repo, right? And the idea here is that it just ran statically on the data that was in there. But as more data is added to the repo, it's going to keep running. And it's going to automatically fire off jobs that commit to those repos that it's already created with up-to-date results of the new values. So I'm going to go back here and unmount, and I'm going to show you this program that I've written, which automates basically the manual thing that I just did to create a commit. And basically all that it does is it starts it in a loop. It starts a new commit using our Go API. It puts some data into sales, and then finishes the commit. And I'm going to have it do this 100 times in very quick succession. And so now when I go back over here and look at the jobs, you can see that there's a ton of them, right? And some of them are running. And as I do this more, it's going to fill up even more. We should expect to see a total of 200 jobs here. So we're at 100 right now. And so what's happening here is while all of this new data is being streamed into Pachyderm, it's automatically firing off these jobs and they're materializing the results. And so this is going to take maybe a minute or so to finish because this is only running on one node. But when it's done, what we'll be left with is a completely materialized view inside of the sum repo. Does that make sense? And so, while I wait for these to finish, there's really no reason that I can't keep looking at the commits as they materialize. So let's grab an advanced commit in the sum repo and see how many of the fruit I'd sold there. So, at that point I've sold 5,800 apples that pumped through the system.
You talking about incrementality?
Yes, good point. So, we talked a little bit a while ago about incrementality in this system, right? And incrementality is this concept that you can take a job and optimize it quite a bit by realizing that you've already done some of the work before and thus not doing that on this run of the job. And so if I look at the commits inside of my data repo, right, I can see, and actually it's, the headings are cut off, but this is the name of each commit, and then this is the parent of each commit. And so you can see that basically these commits go in order, and then each one has the previous one as its parent. So this is just sort of a line of commits, right? And so what that means is that I could, in the next steps, optimize them. I could optimize the filter step by noticing that each of these commits is just the parent of the one before, and by maintaining that same structure. And so indeed that's what happens if I look at now the filter step. I can see that it has exactly this same parental structure. And so the filter step actually never needs to be rerun on any of the data. It's completely incrementally processed. It's a completely streaming operation, even though it was only ever written as just this one job. Cool. That's the end of the show.
I want to see the difference between the first.
The first and last. So let me see if they're all done now. Actually, I can just mount it now. So listing the commits for some reason only takes a little while. But we can see all of them. And then, let's see, how do we find the most recent one? So in final one, 9,000 apples. And then the difference between that and the first one.
Oh, any of those.
Is
So you can run like diff to see what lines were added or removed.
So in the case, so basically what's happening here is like that is basically the single line that was added there. Yeah, in this case, and in the other case, I could show you it's basically all the lines that were appended. But there's always you never delete a line in this example. It's always just additions of lines. So I can just show you those lines.
You can go back and look at the data repo, right? And you would see like, okay, in this commit these lines showed up, in this commit these lines showed up, and you can just go back to your entire commit tree and see exactly which new lines came in. And then each time, only those lines were now processed and summed together back into the sum repo to get the new number each time.
Mm-hmm.
So that means you have to keep like a file system that can handle all the data at the same time. Or you have some way to prune the data when you don't need anymore.
So pruning the data. So you can delete repos within the system, and that will prune the data for that repo out. Deleting a single commit is a little bit harder, right? Because there's like the dependencies and stuff between it. And then there's also a little bit more trickiness that we get into with deletion in our system because we actually do content addressing for our block store. And so what that means is that we can have multiple things referencing the same block, which is a big win because it deduplicates things, but it makes deletion of those things a little bit harder. So right now we don't have a sophisticated enough garbage collection to detect that, and it can be blocked. But yeah, basically you need to have sort of enough space in S3 that you can store all of the data that's been in there.
Not all of that data is like living locally here, right? This is just a mountain.
Sure.
Right, yeah, none of this data is on my MacBook, of course.
So how do we see the history of the data?
The history of the data repo. So this basically is the history of the data repo in terms of all of the commits that have been in it. Right, each of these is basically an immutable snapshot in time. Or sorry, that's of the subrepo, but you can get a similar view for data. So this is all of the commits that have ever been in data. Right, and for each one of these, I can do
Can we like check out like one commit?
Yeah. So I basically have all of the commits checked out by having them in this PFS directory. So I'm going to show you. So there is the sales data for a random commit that I selected. Right, and I can just sort of go ls around the mounted fuse volume, and I can see all of this data inside of there.
Also, you mentioned containers, right?
Mm-hmm.
So, but we're only talking about versioning here. So, container is something runtime, right?
Sorry, container.
It's a runtime thing.
Mm-hmm.
When it runs in a container. Right?
Yep.
So, like if it goes wrong, and I want to go inside the container.
Yep.
Is there a way to like go into the container?
That's the mount command, right?
Yeah, well, so the mount command shows you the data that's gone into it, or shows you the data that's going into the container. You also have sort of an orchestration layer for the container. So for any of the containers, for any of these jobs, I can do path control get logs for the container. And I don't think, I have to spell it right. So they did log a few things. So these were logged by our file system. And so this gives me insight. If anything has gone wrong inside of the container, inside of your container, you can just type path control logs and it will recover the logs from the container for you. You can also, with kube control, so kube control Kubernetes has a program called a job, which is what our job is implemented with. And so I can see all of these Kubernetes jobs that have ever run. And I can then go and look in the pods that Kubernetes has, which remember is its name for the container, and I can find the specific pod that was run for a job. And from there I can find out like anything about the container, and I can execute things inside of it. I can like even SSH into it. What's like you can't SSH it after the fact because it's actually like ceased to exist.
So what is the container right there? Is it Docker or is it something else?
Yeah, this is all running on Docker.
Docker.
Yeah, and the container I made was with Docker. And Kubernetes is designed to be used with other container runtimes, but as far as I know, Rocket isn't fully supported yet.
Okay.
And that's basically the only other one that I know of.
It's Mesos container.
Does Mesos have its own container framework? Okay. I would guess that it's not yet supported by Kubernetes either.
Yeah.
But
Mesos supports Kubernetes.
Yeah. So Mesos supports Kubernetes. You can run Kubernetes on Mesos for sure, and then you can run Pachyderm on top of that, and that should work great. Or
I was just wondering if there's any capacity issues relative to what amount of, say, S3 is consumed by all the bookkeeping and so forth. Do you have an idea of what fraction of the S3 consumption is bookkeeping premium?
yeah. So let's see. Each block is about each block that we store in Pachyderm is 8 megabytes. We reference it with I think something that's 512 bytes. So that'd be about the ratio. Is 512 bytes for every 8 megabytes.
It's really small. It's mostly actually just data.
It should be the vast majority of it should be data, and that's a very tweakable number. I mean, 8 megabytes was sort of a conservative estimate for the right size. We may well crank that up to like a gigabyte. Something. And by the way, one of the other things we get out of using object storage is we can actually sort of use that as a CDN for the entire cluster. So we don't have to think about optimizing for locality anywhere near as much as Hadoop does, because S3 has pretty good performance characteristics just throughout the data center. It died.
Did you do all this in Python, C?
It's all written in Go.
Go.
Yep. Which makes it really nice for interfacing with both Kubernetes and Docker, because they're both written in Go too.
Any REST API for this, if you run this on?
So right now we don't quite have a REST API. What we do have is we have a protocol buffer predefined gRPC API. And so you should be able to compile that into most languages. And we haven't quite gotten to like making an SDK for every language, but we should have that soon.
And logging, do you keep log of the things that you
I do. So and I can even just show them to you. We keep a log of basically every request that happens. So that probably doesn't mean much, but don't worry. There's so much logging it killed it.
Deal breaker.
So is there a rebasing thing? Like in Git we have rebasing, right? Like
Is there rebasing? Not yet. Rebasing is fundamentally it shouldn't be too hard. The thing that makes it hard is that we have to do everything in a distributed system, and the data sets are much bigger than in Git. So in Git you can sort of just like easily delete stuff or like leave stuff laying around, but for us like a commit might be a few terabytes and so that stuff. So not yet. We don't have quite all of the features of Git.
For the underlying cluster run this is run, is that something that you can spin up in EC2 or?
Yeah, so you can easily spin this up in EC2. If you're looking to run Kubernetes on AWS, I recommend kubeAWS, which is a little utility that was made by CoreOS. And it makes the whole process just very painless. Running this on Google Compute Engine is actually even easier because they have this thing called Google Container Engine, which is actually abbreviated to GKE, not GCE, because that's Google Compute Engine. And so that's just like a one-click deploy Kubernetes cluster, and Pachyderm deploys effortlessly on that. Yes?
What's the largest, I would say, data set or kind of pipeline complexity scale that you've tested this for?
So largest data set size, we've tested this only on the about hundreds of gigabytes scale. So we're actually doing like major scalability testing right now to push to the larger limits. Largest pipelines, in terms of, I mean, we've had a number of pipelines created, but in terms of the largest like change between them, I think the largest we've done is like 6 or 7 in terms of actual depth.
Is there like I can keep a socket open so I can send my application can send that data directly to one of those pipelines?
Mm-hmm. Yep, you can just keep a gRPC connection open. It actually even has reconnect semantics, which is nice, so it can like lose connection and it'll regain it. And yeah, you can just use it for a programmatic API like that. Good? Good. All right, thanks so much for having us.